Hi, this is Felipe Flores from Data Futurology. Today we have an extra special episode. We're going to be discussing all things AI factory. It's an episode focused on NVIDIA and all the innovations that they've done. They've got a collaboration platform. They talk about, a sustainable Earth 2.0. We're going to dive into that. So it's going to be a jam-packed episode with a person who has a wealth of knowledge in this industry, an amazing trajectory. His name is Marc Hamilton. He's the VP of Solutions Engineering at NVIDIA. Marc, thank you so much for coming on the show. How are you going today?
Well, first of all, Felipe, thank you for inviting me. It's great to be on your show and talking to the audience there down under. So I'm doing great and looking forward to the show.
Amazing. So to kick things off, tell us a little bit about your background and your current role at NVIDIA.
Well, I have one of the best jobs at NVIDIA, and I've had the same job title for 10 years since I joined. And so my team basically helps all of our customers use our products. And so while the title is the same as when I joined 10 years ago, boy, the job is totally different. 10 years ago, we were just at the start of AI. In fact, it hadn't quite started yet. And so 2012 is when AI started to take off. And so, but the one thing hasn't changed, right, is our GPU platform has been consistent ever since. And in fact, if you were writing CUDA programs 10 years ago on a 10-year-old GPU, it'll still run today. And I wouldn't be surprised some of the audience out there may even have one or two of those old GPUs still running. But of course, so much more that's been developed in the area of AI. We have over 350 different software development kits and libraries and packages today, in virtually all of them in one way or another touching AI.
It's amazing not only the commitment that NVIDIA has made into AI and supporting the community, furthering the technology to make us all more productive and to allow us to apply AI in every realm, in every industry. That's been amazing. But how have things changed during your tenure there? You were saying that you joined towards the early days. How do things look like now?
Well, NVIDIA is over 29 years old. We'll celebrate our 30th birthday next April. And so I've only been here for about a third of that time. But, the first third, we were focused on PC gaming and building graphics cards for that. And then about the early 2000s, when CUDA was developed, it became a way to make the GPU generally programmable in being able to address a wide range of problems. And the early uses of the GPU for programming typically tended to be hard parallel problems that you might find in the high performance computing space at a national lab, a university, oil and gas company, any place that has a lot of parallel code. And of course, NVIDIA didn't invent AI. Modern day AI, the basic algorithms go back 30 or 40 years. You can find research papers on deep neural networks going back 30 years. And what happened about 10 years ago is at the same time, several universities and several students sort of rediscovered those papers and those algorithms. And at the time, we're aware of CUDA and GPUs and the computing power of those GPUs. And they sort of put two and two together. And it was that availability of large amounts of data, which of course by 10 years ago we had thanks to the internet, the compute power of the GPU, and these 30-year-old algorithms sort of reinvented and rebuilt to run on top of the GPU. And then we just saw AI explode. The early uses were a lot of the consumer internet companies and really perfecting computer vision types of tasks. But since then, it moved on to all sorts of things. To one of today's newest fields, is so-called large language models, or sometimes just called LLMs. These programs like GPT-3 that seem to magically invent text or answer questions. And so as we go through the show, I might talk a little bit more about large language models.
Amazing. Thank you so much. So I was wondering if we could dive into the concept of the AI factory. So this is one of the areas that I was hoping we could chat about a little bit. Could you tell us a little bit? I'll introduce the concept and then we can jump in from there.
Sure. Well, AI is a different type of software, right? And it's not actually written by humans. Right. Some of your audience much of your audience may have written some code. They may have written traditional software in C or Fortran or a newer language like Python, or maybe even done some JavaScript or other scripting language, written a macro in Excel, right? In all of those cases, they're typing the commands at the keyboard, right? Taking some input, doing some operation on that input, taking the output. In modern day AI code isn't written that way at all. There's a program called a deep neural network. And again, there's application frameworks that use these deep neural networks to write code. A great example of it would be TensorFlow. TensorFlow and PyTorch are probably the two most common AI development frameworks that you use for writing that AI code. But once again, you're not typing the code into TensorFlow. You're generally taking a large data set and feeding that data into the data set, and then out the other end comes, in effect, that computer code, which then once you have the computer code, that's called training. So you train the deep neural network for a specific task, and then you operate it, you run it in so-called the inference step of AI. So a data factory, right, is just the way that an organization would organize to write code, right? In the old days, you get your developers a PC or a laptop. You might have a file server to store the code, and you'd use GitHub or some other source code control system. And the code was all you needed, right? The software. And of course, with AI, the end code is very complicated. It can't actually be read by a human, but the inputs then are your data. It could be images, it could be video, it could be any sort of language data, or it could be synthetic data, which may be generated by itself by another AI. And so just like if you think of what does a normal factory do, almost any company that manufactures something has a factory or uses a factory. You put in raw materials, you apply expertise from a human or a machine to transform those raw materials into a finished product, adding value along the way. So an AI factory is just a modern way of developing AI code. The inputs, the raw materials, are the data. You still apply domain expertise. The AI doesn't write itself. You have to generate what's called an AI model. And the AI model is what tells the deep neural network, or informs the deep neural network how to actually take that input data and transform it into a program. And then the finished result is then just like the finished result of the factory, and has added value. If you think about it, you start with, if you're a consumer website, you may start with all of your shopping receipts for the day, right? What consumers bought. The output may be a description of what items are the most popular, right? The output of it may be a recommender system that then would recommend based on what was bought that day. When someone else buys one of those items, what do you recommend? Or if the inputs are images of thousands of different lung tumors, the output may be a computer program that then recognizes lung tumors and may recognize the difference between a tumor, a shadow that just represents normal pneumonia, or a shadow on your lung that is pneumonia but impacted by COVID. Very, very slight differences. And of course, we all know that today there's not enough radiologists in the world. So being to augment, make those radiologist jobs easier to do, faster to do, better to do. There's a great output of an AI factory.
It's amazing. It's amazing that's the AI factory is almost like a bit of a holy grail that so many organizations are working towards, and definitely want to make it a reality in more organizations. What would you say are some of the gotchas that people should be aware in that journey of developing an AI factory?
There's, of course, because just like the first factories that were built, right, there was lots of gotchas. One is certainly to don't underestimate the need for data. Now, again, people think of data. You think of some of the early AI programs like AlexNet. It was the first AI that won this ImageNet contest, and ImageNet had for its data set 1.2 million labeled images. So that was sort of the input to the data factory, 1.2 million images that were labeled. Some people say, well, I don't have labeled data, so I guess I can't use AI. Again, there's lots of ways to generate synthetic data. And let me give you an example that is used in our AI factory that we use for building our autonomous vehicle or self-driving car software. If you live in Silicon Valley, or probably in any major city in Australia that has startups in the AI space, you've probably seen some of these self-driving cars, test cars driving around. They've got the LiDAR, radar on the top, a lot of cameras in the front or the back. So you might have seen those driving around. And of course, they're driving around collecting data, right? It's raw data. It's not labeled. And then so that has to go through a process that today can be semi-automated to label the data. So, okay, this was a stop sign, this was a red light. And of course, you can automate that as you go, because once you learn to detect a stop sign with 80% accuracy, then the next time you drive the car, well, 80% of the stop signs can be recognized automatically and labeled automatically, just checked by a human then, and only 20% need to be manually labeled. And they'll continually improve. But of course, it's been estimated that you would need to drive a car about 11 billion miles to drive it on every road around the world in order to have really a self-driving car that could drive everywhere. And then, of course, whenever you made a change to the software, you'd have to drive another 11 billion miles. So if we only relied on cars, even if we had every car in the world collecting data as it drove around, it would take many, many years to collect enough data to train a fully self-driving car. And so, of course, NVIDIA, in our data factory, we not only process the data collected by our self-driving test cars, but we're actually generating data synthetically. And if you think about that, it sounds really complex, but anyone who's ever played a video game with some sort of, car racing or something, well, think about it. The scenes in that video game are simulated or generated data. Now, of course, depending on the quality of the video game, it needs to be a little bit higher resolution to actually test drive the car. If it looks toyish, if it looks really early video game-ish, well, the AI is actually is not going to learn to drive on a real street. So again, it has to be photorealistic. But again, all of that data is generated, right? Just like in the video game, how does the video game know when you turn the steering wheel and crash? Well, because the video game has generated the car, has generated the track, so it knows exactly where it is. And so out of that driving simulation, right, you actually have fully pre-labeled data that is 100% pixel accurate. And again, for every mile that we drive a regular car, we can drive thousands, hundreds of thousands of miles on the GPU and are only limited by how many GPUs we have and how fast they are.
Amazing. That is phenomenal. The work in that space that you guys are doing is super, super exciting. I also wanted to ask you about maybe slightly different topic, but related to that, I wanted to ask you about digital twins and some of the work that you guys are doing in that space. I know that's also very exciting. Could you tell us a little bit about what NVIDIA has been doing in that area?
Sure. The concept of digital twin isn't new. It's been around a long time, but really it was impossible in the past to really put together a true digital twin at large scale, right? And think about it. Let's stay with the car analogy. Think of a car factory, right? The building itself, right, has the blueprint exists somewhere, right? In some form. Think of the car. You have all of the CAD drawings for the car. They exist in some computer program somewhere. But of course, they're not integrated with the blueprints from the car factory itself. And then what do you have inside the car factory? Well, you probably have robots, right? And so robots have, the blueprint for the robot is there, the training, the AI that drives the robot is actually a computer program. So in theory, you think, well, it should be easy to put together a digital twin of a car factory. Well, the first problem that we had, right, is we got fooled a little bit by the internet, right? In the first generation of the internet, right, what we're all using today makes it very easy, right, to click on a website and see the data on that website. Even if your web browser or your laptop has never seen that type of data before or never seen the program, right? That's the beauty of the World Wide Web. It was universal. But the World Wide Web was really about 2D data, right? And there's a whole world of 3D data, right? Think of all the, if you're a designer, think of the 3D design tools that you use. You might use CATIA, you might use Siemens, you might use PTC, all sorts of, commercial 3D design tools, as well as all the consumer or prosumer tools. Think of Adobe, right? How many people use Photoshop or similar type tools? And of course, unlike the web, those tools don't really interoperate, right? Sure, you could take the output of one tool, dump it to a file, upload it into another tool, but it's not dynamic, right? And so to build a digital twin, you really need this dynamic content. And what didn't exist in the past was a universal format, just like HTML was the universal format for the web browser, but it was really basically 2D. And so NVIDIA worked with Pixar, famous 3D company from the movie industry, and helped develop a universal 3D format for doing exactly just that. And besides just sharing the data, it lets you share behaviors. Because think about it, with 3D design tools or a robot, you have the behaviors associated. How far can the arm move? So again, that's the basis for Omniverse. And Omniverse has a program called the Omniverse Nucleus. And Nucleus is sort of this standard database. You very much think of the analogy of the web server, right, that held the HTML data. The Nucleus server, right, can sit in your company's network or can sit out on the internet or can sit in the cloud and can help people collaborate to start with 3D design tools. Now, once you can collaborate with those 3D design tools, you now want to start overlaying the virtual design with the physical or real world. So how do you do that? Well, one, at the start, before the factory is built, you can simulate the factory, just like we talked about simulating the self-driving car. Well, if you can simulate a car racing down your local highway, you can certainly simulate robots moving around a factory or cars moving down the assembly line. So you're now simulating the factory or simulating your physical world. And then once it gets built, even better, through the world of all of the ever-growing IoT sensors, you're now bringing in those IoT sensors. So Omniverse lets you really build metaverses. There's so many definitions of metaverse, but really that overlaying the virtual world that is simulated with the real world, which is measured. And of course, there's all sorts of metaverses, right? People probably have heard of metaverse from a consumer social networking sense. Think of almost PC gaming, and that's a great use of the metaverse, of course. But in a gaming type environment, right? It doesn't have to be exactly physically accurate, right? It doesn't have to obey all of the laws of physics. Versus if you're building a digital twin of a car plant, it has to obey the laws of physics. So the GPU, NVIDIA's GPU, was really the perfect processor for building these digital twins. It's really the only processor in the world today that, one, does traditional math, 64-bit math, very fast and very well. That original HPC work, because when you're simulating the laws of physics, that's 64-bit math. Now, of course, it has to do AI. It has to do AI equally well. And because it needs to be photorealistic, in real time, it needs the ray tracing cores, the RTX cores of the GPU. So being able to combine traditional simulation, AI, and photorealistic rendering in one GPU was the hardware that made it possible. And of course, then millions of lines of code that we've been writing for probably a decade now in Omniverse. We didn't call it Omniverse a decade ago, but some of the building blocks, the visualization, the 3D tools go back that long.
That's incredible. And what does that unlock for organizations when they have a 3D representation of their, say, of a plant or a factory, and then they overlay the information coming in from sensors? What type of doors does that open? What can they do from that point on?
Well, all sorts of things. Let's just say again, even before you build the factory, right? You're going to simulate the robot's going to go bring in the part. Some parts need to be assembled by a human still, and maybe place it on the table or the cart next to the human. Well, of course, workers are in high demand these days. A factory worker, fairly highly paid when they're experienced. If they have to bend down a little bit too far, they're going to more likely to injure their back, right? And so by doing that simulation with a real 3D human, right, simulated again, you can tell how far down you have to bend when you're picking up a particular part. So you may adjust then the placement of that. Other things like even where do you place the different tools, right? You want to place the most commonly used tools, right, sort of at chest level so they're easy to reach. Something that maybe isn't used so often, you might go higher or lower with placing that in the work cell. And again, whether that's a car manufacturing plant or that's a distribution center for a grocery store or for an e-commerce company, right? Think about it. It's what gets purchased today by an e-commerce company or a big store chain is going to change tomorrow if it's raining, right? And so the layout of the factory, right? You could lay out the factory once and keep it that way for maybe 3 months, or you could dynamically change it every night based on how it was done the year before. And so being able to make fine-tuned changes in real time to the factory, to the assembly line, to any sort of task that involves atoms, people, material, places is super, super important. So we think of the meta world as, maybe in social networking is just doesn't involve moving atoms, right? You're just sort of sitting on your couch, on your laptop or your phone. But in the enterprise world, right, the metaverse is going to be all about moving atoms and then overlaying the bits, the AI, the software, the simulation on top of that, and having the bits match the atoms.
That's incredible. The opportunities that come from having good and strong AI, and then the Omniverse combination is the opportunities and the power is incredible. I can imagine for companies that are processing, say, even like a I don't know, a post office or a distribution center, having that digital twin, or in mining, having a digital twin on how things are moving sort of in real time, what are the ways that the work gets done, and then with the AI being able to optimize that, and as you were saying, like optimize the design, optimize the pathways, the way the work is done, the levers that I can pull for organizations is incredible.
Yeah, let me give you one interesting example. In this one, I would have never thought of this use, right? Is again, when you're, think of any sort of distribution center, you have things moving on, boxes moving on a factory line, you're putting things in the boxes to ship. Well, one e-commerce company for the holidays, they changed their tape, right, that they use. You've probably gotten a box from an e-commerce company that's tape with some advertising on the tape. And so they said, happy holidays, whatever holiday it was. And that messed up all of their computer vision algorithms. They weren't able to recognize the tape on the boxes anymore. Now, luckily, they had been using Omniverse and they had simulated this change to this different tape and sort of ran through. And so they caught it before, right, they actually made the change to the tape. Think about it. You're shipping $1 million a day out of a warehouse, $100,000 a day out of a warehouse, and all of a sudden you can't put tape on packages automatically. Think of the cost of that, right? If it's not caught ahead of time. So again, just one really simple example that I love to talk about.
Oh, that's a great one. Super, super powerful. Thank you for sharing that. So now I wanted to see if we could jump to another topic, which I know that you guys are very passionate about, and that's around sustainability. So with all the increase in compute that has happened, that has led to the AI revolution, for us to be able to do digital twins, metaverses, and omniverses, sometimes there's a view to say, well, all this increased computing, it's giving us so much power or so much efficiency in the world, but it's also consuming a lot of electricity. So I know that you guys have been thinking about the sustainability side of all this. Could you tell us a little bit about that side?
Sure. First, let me. I'm going to talk about how we build our systems and some of the sustainability there, and how we're going to study some of the impact. But again, all of these examples in this next one are all ones that really NVIDIA didn't do themselves, right? We really focus on building the platform, right? Whether it's Omniverse, there's a platform for building digital twins, or it's Merlin, which is our platform for building recommender systems, and onwards. So the example of the car manufacturing plant, the e-commerce distribution warehouse, those were all customers of ours that built things. One of the really interesting use cases of Omniverse that is directly related to energy efficiency was around 5G design, 5G cell phone towers. Today, in a 4G tower, right, what happens is the phone company will come in and they'll drive through the city and they'll survey it, or they'll have it all digitally, and they'll decide where to put the 4G antennas. And 4G antennas are directional, right? So one may be pointing down the street, et cetera, but that direction doesn't change, right? They sort of point the antenna and they leave it there. And of course, one of the big advantages of 5G is that you have, with more advanced antennas, they can be directional. So via software. So without physically moving the antenna, right? In the morning, the antenna may be pointed on the side of the street. There's the incoming traffic coming into town, in the afternoon coming out, right? When people are walking, into a building, right? Versus going out at lunchtime, right? Different patterns. And of course, though, with 5G now, you need to have, or with any sort of technology, with any sort of, technology as far as cell phones, you need more and more towers. I'm sure in your neighborhood, you've seen them putting up some towers. And of course, not all towers are the same, right? You're able to go through and change the power going through that antenna in the tower. What one what one cell phone equipment manufacturer did is they simulated a whole city. They had mapping info of all the cities and of a city. And think about it, a cell phone signal, right? It bounces off of a glass building differently than a wood building. It bounces off rain when it's raining. Very sort of complicated simulations. But in effect, right, by placing a lot of different towers, a lot of different cell phone antennas of different power levels, and by going through and simulating all of this with a digital twin. And again, just like we can simulate a car going down the test track, right? We can simulate cars driving in and out of the city. We can simulate pedestrians walking into a stadium, walking into an office building. So you can actually go through and support the higher 5G bandwidth, support more connections, but do it with lower power antennas, even though you're actually placing in more antennas. So remember, two parts of energy usage, right? One is the training part, and we always think, well, the training is where you have all those GPUs and using all of that power, and then of course the running or the inference, right, of it. So again, when those radios get deployed, the cell phone radios, that sort of that inference part. And so again, fundamentally, the first thing I always remind people is that, well, a GPU, right? Think of our consumer GPUs. They might be 200, 300 watts versus 100 watt for a PC CPU, or maybe even 20, 30 watts for your laptop. And people say, well, the GPU is more powerful, so it must be wasting energy. It actually isn't, right? Because again, when you use the GPU, you're using it for tasks that would take 10, 50, 100 CPUs to run. So using 100 watt CPUs versus using one 300 watt GPU, obviously the GPU is a lot more effective. But anyhow, like I said, Omniverse is a platform we built. We use it internally for running our own internal business, but it's really a platform that we work with customers. We show customers how to use it. We show our partners how to use it, and then they go solve these interesting problems. Some problems are so hard and are of interest not only to all of our employees, but to basically everyone on the planet. And that's really studying climate change in energy transition, right? Again, everywhere in the world, people are thinking, how do you transition to different power sources, to energy sources? That's, of course, directly impacted to having impact on the planet and climate. Today, as we speak, all over the world, right? In China, in the US, in Europe, there's rivers at record levels, in record low levels. Now you're in Australia, so it's not the summer season there yet. So you haven't suffered from that yet. But Australia had all the wildfires a few years ago, right? And Australia certainly has a water problem already in many parts of the country. So what is the climate change going to mean to Australia in 50 or 100 years? And think about the weather report, right? Well, the weather report for today in Sydney or in Melbourne is probably pretty accurate, right? Usually, they may, if it says rain at 5, it may rain at 4, but usually it doesn't rain if it's not in the forecast. You can leave your umbrella at home. If you go out a week, you can get the weather report for a week, but it's a little less accurate. Right? It certainly, may say 20% chance of rain on Friday, and then it ends up raining on Friday. But think about climate. You need to simulate not just for 7 days, but you need to simulate for 700 or 7,000 days, right? You want to look out 20, 30, 40, 50 years out into the future. And that's what we call a so-called million X problem. We can't solve it today. Right. And we know that we need to be able to compute about 1 million times faster. So building a global climate model in inside Omniverse, building a digital twin of the Earth, in effect, is a project that we kicked off about a year ago. Mm-hmm. It's going to be many years before we're done, but we're already making some interesting progress and see some interesting early signs of future success with Omniverse. as far as that. And we call that project Earth 2.
I love it. I love it. The scale of the ambitious projects that you guys take on is incredible, and it really helps us continue to develop the industry and the capabilities. So thank you very much for that. And additionally, I really liked the discussing with you that GPUs are a more energy efficient way to unlock the power that we're able to from AI, from Omniverse. That's fantastic. But then additionally, there's benefits on the optimization that the AI can bring on systems that are live in production. And that example around 5G, that's phenomenal, to be able to make the transmission of information more energy efficient because it has been optimized through AI. That's phenomenal. And then taking that up a notch, or maybe a few notches, to Earth 2. That's a humongously ambitious project. So super exciting work that you guys are doing, as always there. And I did want to ask you, for organizations that are either dealing with these challenges or thinking about these challenges, at what point should they think about reaching out to NVIDIA or to your team, or how can people get involved in getting some help to look at areas like the ones we've spoken about today?
Well, first of all, we always love it when customers reach out to us, right? We have, one of the things that we've learned to do even better while we were all locked up for a few years during COVID is to work remotely with our customers. And in fact, think about it, pre-COVID, right? You probably did some podcasts, but, most people wouldn't necessarily think of working with video. It wasn't commonplace. And today, everyone does. So there's a lot of ways to reach out. We have offices around the world, of course, and you can look us up. Most customers reach us online. In fact, today, we run what we call NVIDIA Launchpad. You can just go to launchpad.nvidia.com. And what Launchpad is it's where we launch all of our new hardware and software products. So the first place we ever put any new software, first place we ever put any new hardware is in Launchpad. So again, those 350 different software programs, those all exist on Launchpad for customers to try out. And earlier this year, we announced our latest and greatest GPU architecture, the H100 Hopper architecture GPU. And so, a lot of customers have been saying, well, when am I going to see a Hopper in some of the big public clouds? Coming soon. Go ask them. When will Dell or HP ship me a Hopper-based GPU? Coming soon, but go ask them specifically for their ship dates. But probably the first place, very, very soon, where you'll see the H100 show up is in NVIDIA Launchpad. So we're very excited about making it available there, and you'll hear all of the details on it. And I expect it'll be right around the time of our upcoming GPU Technology Conference, which is now only about 5 weeks away, coming up the second week of October.
Super exciting. Marc, I want to thank you so much for spending this time with us today, for sharing your knowledge, your experience, your perspectives, and all the exciting work that you guys are doing at NVIDIA. It's mind-blowing, the ambition of the projects, the scale, and how much you guys are pushing the envelope forward for all of us to leverage. So yeah, a huge thank you. And this has been an absolutely wonderful conversation.
Well, great being on the show, and I hope to come back again after we've done a little bit more work on Earth 2 and give you an update.
That would be amazing. Thank you so much, mate. Thanks for watching this video all the way to the end. I hope that you got a lot out of this discussion. And if you're watching on YouTube, please like and subscribe to the channel so more people can find out about the challenges that leaders have in the analytics and AI space. And that's what we're trying to share in Data Futurology. So please like and subscribe. And if you enjoyed today's episode, please tell your friends. Thank you so much.